kind of stuff, yeah, we can also do that at whatever.
Okay. Good afternoon and welcome to the Simon's Electron Microscopy Center's Winter EM course. We are rounding out our EM crystallography section with MicroED today. And I want to remind you, so we've gone over 3 different modalities of EM. We went over tomography, single particle, and now crystallography. And I want to just empower you with these tools in your toolbox because with the same instrument, the TEM, you can collect all 3 different types of modalities. And Fernando mentioned yesterday that maybe helical might be a little bit niche. You might find MicroED a little bit niche. But if you're in a field that uses it every day, then that'll be your bread and butter, and that'll be quite useful. So the idea is to give you options so you know that despite you might be using one modality right now, you can be free to grab other tools in your toolbox, as it were. Okay, so today's speaker is Bill Rice. Are you not picking up anything?
I can't hear you.
You can't hear me? Because my mic just died.
Battery?
My battery.
Oh,
so
no,
that's my battery.
That's
Not Bill's battery. That's fine. Useless anyway.
No, we can hear it.
You can hear it?
Go back, yeah.
Go back. Okay. I don't take instructions that long. So let's move on. So today, the speaker you've heard before, our EM manager, Bill Rice. He's going to tell you about a technique that's been growing in popularity right now, primarily because it's the technique that can break the angstrom resolution range quite routinely. And if you're working on a particular system like a peptide and amyloids, this is perfect. This is exactly what you would want to use. Okay, so I'll hand this back to you, Bill Rice.
Thanks. This is MicroED, not MicroED.
I'm smaller now.
Nerd jokes.
So as Ed said, this is the last of the, I think this is the last of the new techniques we'll be talking about in this course. So we started with tomography, and that can get to, maybe, I guess around 5 to 10 angstroms at least with subtomogram averaging, probably around 20 angstroms without subtomogram averaging at best. As you are familiar with, single particle is certainly by far the most popular technique right now, and its limitation is right now around 2 angstroms, so it's a little bit better. 2D electron crystallography, which you just heard about, has gotten to 1.9 angstroms, although that's become a little less popular because it's, as probably you heard from the lecture, it's a little bit harder to deal with than single particle. And then finally, MicroED is now at around 1.0 angstrom is the highest resolution from that. So but the best resolution from EM from any of these techniques. So that's probably one of the main interesting things about it, is that it gives, right now, the highest resolution. It might be in another 5 or 10 years, single particle might be there, but certainly right now, 2.2 is pretty hard to get. There aren't very many structures that are at that level, and I would say most structures are around the 3 to 4 angstrom range. So MicroED, if you really, really need the best resolution, that might be the way to go if you can get crystals of your protein. So this is a little graphic of the various structures that have been solved by MicroED. The first one that was solved was in 2013 was lysozyme at 2.9 angstrom resolution, and then that slowly got better as the technique improved to 2.5 angstroms. I guess the largest ones that have been solved are catalase at around 3.2 angstroms in a couple of different labs, and then also the calcium ATPase from Toyoshima's lab was also solved by 3D at about 3.5 angstrom resolution. Lately, the highest resolution structures have been these tiny little peptides, and those are the ones that have gone to 1 angstrom resolution. And so those are the ones that those are more I guess most exciting ones because they're getting to the highest possible resolution. When the technique was introduced in 2013, that was kind of right before you might call the resolution revolution. So that was when direct detectors were just coming out, and it wasn't really clear that single particle would ever get this high. And so that was, this at that time, that was the best way to get a high resolution structure. Since then, of course, with direct detectors, you can get to 3 to 4 angstrom fairly routinely now, and better than 3 with really good proteins. This sort of shows, in this paper, they sort of tried to show it as a growing trend. So between 2013 and 2017, it's growing, I guess, exponentially. but it's still not very many structures, about 25 altogether. If you compare the total EM structures, they're around 4,000 altogether, 4,500. And on the right-hand side of this goes only until 2016. I'm sure right now it's way up here. But if you look at by method, the vast majority is single particle. You have a little bit of helical, a little more subtomogram averaging, and then just straight tomography. And then crystallography is still a very, very tiny part still of the total EM structures being solved. So there aren't that many people doing it, but it is a potentially interesting technique. Certainly, if you do have crystals of something that don't diffract very well, this might be more interesting for you. It's probably better if you're coming at this technique from a crystallography background than from if you're new to structural biology, because then you have not only have to learn the EM, but then you have to learn sort of how X-ray images are processed. And then this is again just another map of all of the various structures solved by MicroED and their sizes. So I guess the best is 1.0. The ones that have gone the best resolution are all these tiny little peptides, and these would be by far impossible by a single particle. They'd be completely invisible. And then there's some maps of structures. So yeah, this is the one this alpha-synuclein, which is involved in Alzheimer's. They sort of crystallized what they call the toxic core of it, this little very small peptide branch of it, and it formed these tiny, tiny crystals that actually were invisible. They're basically on the order of a micron long, but only about 50 nanometers in the other direction, and then maybe only 50 or 100 nanometers thick. So they're tiny, tiny, tiny. They couldn't even see them by screening by regular light microscopy. They were basically invisible. The only way they saw them was putting it on an EM grid, and then they saw these little crystals, and then this is a diffraction spot of one of those crystals. And if you look at the diffraction pattern, the resolution went out to was visible in this picture to 1.5 angstroms. And I think this is one of the structures that went to about 1 angstrom resolution. And this is how a picture of some of the crystals. So some of them were visible by light microscopy, but in general, these tiny ones were only visible by EM. Oh, yeah.
So I heard that for doing MicroED, you are essentially limited to using tiny crystals.
Yeah, they have to be thin, for
What
sure.
What is the reason behind that?
I'll get into it a little bit, but basically with the thicker crystals, you start to have more double scattering events, which don't obey the right optics, and also more inelastic scattering events, which also don't obey the right optics. So you just don't get enough through it, or what does get through it has been scattered a couple of times, so it's no longer at the right point where it should be. All of the diffraction theory assumes only one scattering event. So if it scatters twice, it ends up contributing to the wrong spot, and then that messes up your intensities.
And what is the limitation, like the upper limit of like size-wise that can be used for MicroED?
For protein or for
protein?
Yeah, so that also, I think there is a bit of a
crystal-wise. I mean, like what are the biggest crystals you can put on a?
Oh, I see. Well, so it can be microns long. It can be like on the order of a couple microns long, or 4 or 5 microns long, but it has to be thin in the direction that the beam is going through.
Yes.
At least in some of it. Of course, it will. If it's long and very flat, that would also be a problem, because then as you tilt it, it's going to appear to get thicker. But in practical terms, they found that about 400 nanometers for lysozyme crystals was the limit. I guess there are some theoretical papers that they calculated the limit should be closer to 100, but that seems not to be true. In practical terms, 400 seems to be about the limit, at least for lysozyme. But they do have to be. You do want small crystals. But on the other hand, if you have big crystals, you should probably just do regular X-ray diffraction. There's sort of no reason to be trying this on a crystal that you can normally put into an X-ray beam, unless for theoretical reasons, of course. This is the structure of this amyloid core again. So this was solved at around 1 angstrom resolution. So they were able to see how these beta sheets were packed very well with each other, and they sort of hypothesized based on the structure of this that because of the way these things are packed, the crystals, it induced some sort of strain into the crystals, so that it was impossible for them to grow to a large size. So that was sort of why MicroED was essential for these types of crystals. How applicable that will be for other things is not entirely clear yet, because I think a lot of the, in a way, part of the joy of single particle is that you don't have to make crystals. So anyway, so just to get into it, I don't know do many of you have a background in X-ray crystallography? Probably a lot of you do. Anyway, you did recently get the electron diffraction, or the 2D electron diffraction lecture from Ewald a couple of weeks ago. So basically, in terms of diffraction theory, you have the Bragg diffraction theory. You have your molecules are modeled as sort of a bunch of scattering points, and then you have an X-ray or incident beam coming in at some angle theta, and then it gets deflected at some angle theta, and you only get what you want is to get constructive interference, and you only get that when their path length is such that the two beams are in phase, so that you don't get destructive interference, you get constructive interference, so that they're then add and get you into those diffraction points. And so from Bragg's law, if they're separated by a distance d and it's scattering at an angle essentially 2 theta, the wavelength of the beam that's coming in, which is lambda, has to be some multiple of the wavelength has to be equal to 2d sine theta. So the basic equation is n lambda equals 2d sine theta, and that sort of defines where the diffraction spots will appear. And this is how X-ray diffraction works. In an X-ray, you just hit it with an X-ray beam, you look at what diffracts, and then you collect diffraction spots. And so this is what an X-ray diffraction pattern looks like. I'm not sure if you actually do an X-ray experiment, you actually see this, or everything is done by the computer now. But
You still see
you
it.
still see it?
Yeah, you gotta see the
I'm not
diffraction.
sure. I guess so.
Because otherwise, then you're like, well, go on to the next
Doesn't work.
crystal.
So in terms of a diffraction pattern, this is, if you remember, this is basically in a way this is a reciprocal or Fourier space. You always have a beam stop which blocks the direct beam, because most of the beam is not diffracted. So this would be a very, very intense beam that's going right through the crystal. So you always have to block that with a beam stop so that you don't end up burning whatever detector you're using. And then this is the sort of it's not just a single point, but it has to be held by a wire or something in place. So that's why it blocks out a little region here. So, but what you end up getting is a whole bunch of reflections or diffraction spots on your detector. And what you also collect in X-ray is you only collect the intensities and the positions of these spots. You don't get any phases. There's no way to collect phase information from this. All you get is the positions of it and the amplitudes. Now you only get, this would just be from one particular view of the crystal, and what you actually have to do is you rotate the crystal in the beam and take a whole bunch of pictures of it to get all of the different views and diffraction spots. Generally, I think you rotate 180 degrees to fill Fourier space. If you have some symmetry in your crystal, you technically don't have to rotate the full 180 because you can take advantage of the symmetry, and then you can rotate less. I'm not an X-ray crystallographer, but my understanding is in general people do try to rotate the full 180 to collect the full data set.
You get redundancy.
Yeah, it also helps with more.
Yeah, so you go until your crystal dies, basically.
Right.
Even more than 180.
Yep.
Right, so a little bit more, so just make sure you cover it.
180 is basically, you're technically...
Barely enough.
Yeah, Friedel symmetry, right? So then you only have to go 180.
Right.
It should be complete, but never is.
So from the positions of the various spots, you can get the 3D lattice parameters, but then you have to do phasing. In order to actually calculate what the structure is of the molecule that's filling up this lattice, you have to get the phases right. And I think that's also been gone into pretty well in all of the lectures in the course about the importance of getting the phases right. So in order to get the phases, there are several different techniques. If you have a very small and not complicated crystal and it goes to very high resolution, you can do what's called ab initio, where you computationally figure out what the phases are. I don't think that's done very often except for small crystals and ones that go very, very far. The other more common way is if you add heavy atom derivatives to your crystal structure, and then you see where these heavy atoms scatter, and that helps you get a starting point for the phases, so that you can sort of solve this puzzle, or the computer software will solve this puzzle to get the phases right. There's also anomalous diffraction, through the MAD and SAD techniques, where you replace methionine with selenomethionine, and you then look at the diffraction, you change the wavelength a little bit, you sort of see the anomalous diffraction from this selenium atom, and then you sort of get phases that way. And finally, another way is if you already have a high resolution structure of a protein which is similar, but not necessarily not identical, but similar enough, you can use molecular replacement methods where you sort of put that use that structure as your starting point, determine phases from that, and then iterate until it converges onto the right answer. And so this is what's been done in X-ray crystallography for decades, and these are all very standard techniques, all very well understood. I guess ab initio is getting better and better as energies get higher and higher, and data gets better and better. But most things, I think, are heavy atom derivatives, MAD phasing, or SAD, and molecular replacement. So one other complicating thing is what's called the Ewald Sphere. So this is sort of a theoretical sphere in Fourier space of radius 1 over lambda, where lambda is the wavelength of whatever of the radiation you're hitting it with, surrounding the crystal. And so if this is the sort of diffraction spot in 3D space, I'm only showing 2D because it's easier to show a circle than a sphere. You only actually get diffraction spots where these lattice points interact with this Ewald sphere. And so the radius of it depends on the wavelength, so you can have, I guess these are two common wavelengths used in X-ray crystallography, and so depending on the wavelength, you'll have a different size Ewald sphere, and so you'll get different diffraction spots and different orientations of it. And what you actually have to do is you rotate the crystal in the beam, and then that sort of rotates this through this lattice to get the different diffraction spots. And that sort of leads to these sort of, the sphere sort of leads to these curved lines of diffraction spots, because the interaction with your detector is basically a plane, and that's interacting with this 3D sphere, and so the interaction of the plane with a sphere is a circle. So when you rotate the crystal, you sort of rotate this little sphere around this origin O, and it will sweep out this area that's marked in yellow, and so that you'll be able to get all of these diffraction spots that are marked in yellow. But these points which are further out, this would be even higher resolution. These would be sort of too high to interact to be able to collect with a beam of this wavelength. But so basically you're still limited by the wavelength of the radiation that you're using. This is all sort of very basic 3D crystallography, and hopefully you're all familiar with it.
I think it's a restatement of the Bragg's law, right?
Yes, it's another way. Yes, indeed. Yeah, because it's another way. Yeah. Again, I'm not a crystallographer, but I've done a little bit. But our thing never diffracted well enough to solve. Just sort of. So one other thing that is actually done in X-ray crystallography is the crystals actually oscillate a little bit. So when you're collecting the image, you rotate it by a fraction of a degree or something like that while you're collecting it. And so in a still image, you'll get the first order layer lines in this circle, say, or first order diffraction spots in this circle, and second order in this circle. If you oscillate it, then the positions of these circles change. So this is the original position in solid, and then the moved position after you rotate the crystal is in dotted lines. And you get, if it's oscillated a little bit, you'll get sort of data. You'll get diffraction spots all between these two things. These are what are called Lumens. And so this is actually what you actually collect. The thing is, because the sphere only interacts discretely, if you only image at very discrete angles, you might miss some diffraction spots. But if you oscillate it a little bit, you'll sort of fill in all the space, and then you'll get everything. So that's practically what is done in X-ray crystallography. And I think that's pretty much all programmed by whatever beam line you're using, or maybe set parameters, I'm not sure, but anyway, it's all, again, this is all very standard and well understood X-ray crystallography for a long time. Okay, so here's what it practically looks like. So this would be image 1, where this would be sort of an unoscillated image where you see just discrete diffraction spots, and they're sort of appearing in circles. And then you rotate it by a few degrees, and this one is also taken with some oscillation. And then everything has sort of, it's sort of moved a little bit, and you actually start to see, because you've rotated it a little bit, you start to see these first order I'm used to helical, but these first order diffraction spots which were invisible from this particular view. And also you see, because of the oscillation, you sort of fill in a little bit. These are sort of the lumens in here. And then the other things have shown up out here. And so this is sort of, again, this is what's done in X-ray crystallography. So limitations of it, as probably you're aware, a lot of proteins actually you can't get crystals. And from about 10 years ago, I'm not sure if this is actually still a high number or not, they said that about 30% of proteins that crystallize actually don't diffract a high enough resolution, so they're just no good crystals. Another technique is if you have really, and then the crystals also have to be big enough, although that's, with higher and higher better and better beam lines, you can get away with smaller and smaller crystals. There's also a technique called X-free electron lasers, which use a really, really high powered beam to just sort of, you take one shot, you destroy the crystal in that one shot, you collect everything from that, and you image many, many crystals that way. But that one you need many, many tiny crystals, and it's also a fairly expensive experiment because there aren't many places that, there's only 2 electron-free lasers in the US, I think. Something like that, I'm not sure, but it's kind of even more of a niche experiment. So getting back to EM. So the wavelengths, again, you're probably familiar with this. X-ray wavelengths are, say, 150 picometers. But EM wavelengths are much, much smaller. So even at 80 kV, you're at 4 picometers, and at 300 kV, you're down to 2 picometers. So EM is definitely not wavelength limited for any sort of diffraction. And even, you don't even need a very powerful electron microscope to get very, very tiny wavelengths. The difference between 80 kV and 300 kV is not a big difference. What you do need is a good source. So you still need a decent microscope, but you don't need high voltage. So this is, again, you probably should be familiar with this sort of image by now. This is sort of standard optics, of electron optics, where you have the electron beam coming down, you have your sample inserted in the microscope. It then gets diffracted, or it gets scattered by the electron beam is scattered, and then goes focused by an objective lens, and you get in the objective plane or the back focal plane, you end up getting a sort of a diffraction pattern of the image, or a Fourier transform of the image. That then gets reconstructed into a real image, and then is magnified by the projection lenses to form a much magnified image at the very bottom. This is the standard technique that we're all using in EM for regular imaging. So it's slightly simplified diagram. What's important is in the objective plane, you usually have an objective aperture inserted, so that you're getting rid of the most highly scattered beams. On our Titan Cryos, the 100 micron objective aperture is just outside the 1 angstrom limit. On other microscopes, you might be trying to enhance more low resolution information, so you might be scattering at 5 angstroms or something like, illuminating worse than 5 angstroms or something like that. Depends what sort of imaging you're looking at. And then there's also something which we generally do not use as a selected area aperture, which is in the imaging plane. And so that limits what actually you see. So you can actually, in terms of regular imaging, there's really not much reason to use a selected area aperture, but in terms of diffraction imaging, there is. So in diffraction optics, you have your beam, you have your sample going through. Usually, if you're collecting diffraction images, you don't have anything in the objective plane because you want to collect even the most highly scattered spots, so that you actually see the highest resolution you can get. But then in the imaging plane, you have a selected area aperture inserted. And the idea of that is you want this inserted so that you're only looking at your crystal, it's sort of set to be the size of the crystal or something like that, and not bigger. So if your crystal is 5 microns or something like that, you might put in like a 10 micron SA aperture or something like that, so that you're not getting extraneous information from the outside area. You, instead of having projection lens turned on, you have the lenses are set so that they basically become diffraction lenses, so that instead of an image forming at your detector plane, you end up getting a diffraction pattern formed, and you collect the diffraction spots on your detector. You also then have to have a beam stop inserted. That's just that little pointer, which is on all scopes. And you center that so that your pointer will block out the unscattered beam. Otherwise, you'll burn through your detector very quickly. So this is sort of the setup for diffraction imaging. It's actually, in a way, it's easier to set up this than for regular imaging, because you sort of have less. You're not forming images. You're just collecting the diffraction patterns. You want to make sure that the main thing is to limit the diffraction astigmatism and make sure the diffraction beam is going right down the center of the column, but you don't have to worry about various other like objective astigmatism and things like that, because you're not actually collecting images, you're only collecting diffraction spots. The other thing is, because you're only collecting diffraction spots, you're no longer sensitive to sample drift, because you're not collecting phases, you're just getting amplitudes. So if the sample moves a little bit, those spots stay in the same spot, you're just collecting them. So you don't actually care if the sample is moving a little bit. Obviously, if it moved a lot and it left the actual imaging area, then that would be bad. But as long as you're much less sensitive to drift. So this is one of the reasons why it was easier to get higher resolution structures earlier from, say, 2D crystallography than from single particle. There are 2 possible modes of collection, which I'll get into in the next few slides. The first mode, which was the earliest one, was sort of more like a tomography type experiment, where you would take an image, then tilt the sample a little bit more, take another image, then tilt the sample a little bit more, and then keep collecting that way, keep collecting sort of still diffraction images. The other way is to actually, if you have a camera that has a movie mode, you collect a continuous movie, and you can, as you're collecting this continuous movie, you continuously tilt the sample, and then you're sort of then, instead of getting discrete angles, you're then filling in all of space here, and so then that becomes, the advantage of that is you then are sort of filling in the Ewald sphere naturally. You're not going to miss any information, unlike if you just tilt it discretely. And so this is sort of what's done now. This has been done. This was the original experiment, and this is sort of more what's been done now. You have to have a camera, though, that is fast enough to collect these movies, and you have to have a stage that lets you continuously rotate or tilt your sample at a defined speed. So those are the main 2 complicating factors for that. The other thing is you're sort of, because you are still have your sample in the holder, in the microscope, you still are not free to tilt to 90 degrees, unlike with X-ray, where you could go from -90 to +90 or a little bit more, and you get full 180. With a standard electron microscope, you're basically limited to -70 to +70 degrees. There's not too much you could do about that unless you develop, you had something where it was on a pin or something, but
It was an idea.
that would be hard. Yeah.
Is there any way that like symmetry could help you with this missing wedge, or potentially I could see
So
merging multiple crystals?
Indeed, yes. So you could. I mean, you could collect a single data set, and then if you know your symmetry and you figure out your crystal orientation from your first picture, you could figure out a way to collect it such that you fill in the missing wedge because of symmetry arguments. But that could be a little bit hard, and practically what you do is, I think, you collect multiple data sets on multiple crystals. And then, because generally on one grid you're going to have a lot of crystals. If you only have one crystal, it's going to be like impossible to find anyway. So usually in this sort of experiment, you'll have a lot of crystals, and you collect multiple data sets. Hopefully the crystals are lying in different orientations on the grid. If they're not, then you might have to take care of symmetry arguments, or you might be sort of stuck where you actually do have some missing data, and then that will sort of blur out your resolution in one direction. Similar to what happens, the same thing that happens in tomography. So yeah, if your crystal is thin in only one dimension, so that it's like super thin, but then wide and flat, that would be a difficulty, because then it basically would not lie in the right way that you could do it.
So this is like a similar problem with like 2D crystallography, I guess? 2D
crystallography also you can only tell -70 to 70, yeah, but with 2D is sort of worse because they're naturally only they only are 2D. They're not 3D crystals, so there can only be essentially one way they can be lying in the microscope. Getting to crystal thickness, yeah. So you can get diffuse scattering in case the crystal is distorted, or you get inelastic scattering. So the thicker the crystal is, the worse the inelastic scattering is going to be. If you have a scope with an energy filter, that could help mitigate it. And also if you did it at a higher voltage, that could help mitigate it. But still, you're going to be limited by inelastic scattering. This for the lysozyme crystals, the 400 nanometer limit, that was done on a 200 kilovolt Techni F20 without an energy filter. So if they did it on it might be that if you did it on a 300 kV scope with an energy filter, that would help. The other trouble is dynamic scattering. So if the inelastic scattered electrons have a second event, then there's not much you can do about that. You can't filter that out because they're still inelastic, and they'll just sort of contribute to the wrong spot. So then that'll sort of mess up things. So there's nothing you can do about that. So you're limited to in the original paper they said about 400 nanometers. And so I have a feeling this technique, it really is for small crystals, not for things that grow big. Again, if you have something that's big enough, you would probably you're better off going to a beamline and saving all this complication. On the other hand, if you do have crystals that are large but imperfect, one thing they did was kind of break them up, and then you sort of have this crystal that's sort of this heterogeneous bunch of sort of little things, and then you break it up by some way, by beads or by just pipetting up and down. It depends on the crystal. You have to sort of figure out. You have to sort of manually figure out what is the best way. And this was done for a couple of different proteins, tau segment or trypsin, and they found that after they broke it up, they could then get high resolution diffraction on these tiny microcrystals. After breaking it up, they may well be almost invisible. So you sort of are stuck at the screening stage to put it on a grid and see if you've actually made them small enough that you actually get crystals on it. So some more details about the work overflow. So basically what you have to do is, first of all, identify that you have microcrystals. So if they're not too small, hopefully you can see it by standard techniques that they use in X-ray crystallography. So just using a light microscope to see if you see some sort of powder or cloudiness.
I don't understand how at the beginning they put on crystals that were invisible. What prompted them to do that if they can see it?
I think that for some of them, I think they were able to see some tiny powder or some sort of precipitate. So then they just sort of thought it was they eventually would get some sort of precipitate, so they decided to see what was in it before it precipitated, I think. So I think that was how they sort of knew. But yeah, it's kind of...
Because then I was thinking, I'm sure there are always some sorts of nucleation points for crystals to form. It may not grow enough for you to ever see it, so...
Right, yeah. So with crystal, yeah, it's true. I mean, when you set up a thing at a very high protein concentration, you may have some little nucleation points. We see that with our 2D stuff where they suddenly form these filaments or something like that, which would be too small to see. But it has to be still sort of macro enough that it's actually forming a thing, like an actual crystal. What I think with that experiment, what they did, if I remember right, they saw some precipitate. They didn't see crystals, and so they just sort of edged it so that just on the edge of precipitation, and then they could see things.
And also you mentioned that the thickness of the crystals is, in this case, it's bad if it's too thick, because you said it in
Thicker than 400 in the Z direction is too thick. Yeah.
Because the that's very different than crystallography, where if you have very flat crystals and they're not three-dimensional, isn't that a concern for collection as well?
You mean if you don't have enough enough unit cells in that direction? Yeah, they do have to be thick enough that you get enough unit cells that you actually get diffraction. I'm not sure.
You know, that's
I mean,
not that's
well,
not
like
true.
if you only had 3 layers. I remember I worked on crystals where I had like literally there were very, very thin 2D crystals or 3D crystals, but they were like literally 3 or 4 layers thick in the Z dimension, this calcium pump. And so those ones cause trouble because if you only have a few layers, then it all blurs out. So how thin it has to be, I mean, it has to be thin enough that you still get, it reduces to spots.
I think Tobias said that 8 layer lines is good enough, so he did.
Oh, 8 is, oh, okay.
Yeah, he did support 8 and 1. So I don't know how, that's the limit that he has said. Yeah.
Well, in principle, planar geometry should be okay, right? Because 2D crystallography also works.
But
But they-
2D crystallography, you're not taking, but this is a 3D method, so you're assuming this is, with the 3D crystallography, you're tilting it so that you're getting the other dimension.
Oh, I
But
see.
if it's too thin in that direction, those are just blurred out. So
Yeah.
so if 8 is the limit,
But
I
also,
mean 8 would be pretty thin still.
for 2D crystallography, isn't it often that they take an image as well and they use the diffraction patterns just for the phase?
Yes, but
So-
that only works if you have 1 layer. But if you have 2 layers, it's a mess. If you have 2 or 3 layers.
Oh, I thought you can't just, I thought it was limited to 1 layer for 2D crystallography, isn't it?
1 layer, yes. 2D crystallography is only 1 layer, and then you take images to get the phases and everything like
Yeah.
that, and you also tilt it.
Yeah.
But if you have very thin 3D crystals that are fewer than, if it's only like 3 or 4 layers
Right, I'm
thick.
just saying that's why for 2D crystallography, that's probably why it's fine if you're taking the images themselves, and you're just using it for.
Right, you don't have anything overlapping in that other dimension.
Yeah.
But the thing is, once it becomes thick, once you have 2 layers, then you get overlap when you tilt it,
Mhm.
and then that messes you up that way. So you no longer have this sort of tilted 2D diffraction pattern.
Yeah.
You have these sort of interfering patterns, which are not enough to constructively interfere properly. So it's not this sort of hybrid becomes a very complicated problem. Actually, one of the people who worked in Tamir's lab, Dan Shi, and he used to be in the same lab where I was a postdoc, and he was working on these thin 2D crystals of calcium pump that were like 2 or 3 layers thick or 4 layers thick, and it was a real. He had to write all this software to try to index the thing, and it was almost impossible. And the eventual solution was make them thicker and get 3D crystals. But then although they did later on, this Japanese group, Toyoshima's group did do this MicroED method of these calcium pump crystals, but they must have still made them thicker than the 3 or 4, because it was very hard to actually process these slightly thick crystals, or ultra thin crystals, I guess. But yeah, it's 2D crystallography is probably the hardest technique, I would say, in EM, because it's sort of the least worked out. The software is sort of, I would say, the least mature, although there have been a lot of work to make it more user-friendly. But I remember it used to be, some of the unit cell constants were sort of in the Fortran code itself. So you had to sort of know the code and reprogram it for your crystal. But it's better. I'm sure it's better now. I mean, with Henning, they've written 2DX was a lot better. That was about 10 years ago. But anyway, for thin 3D crystals, what you have to hopefully identify your crystals by some sort of light microscopy, or just put them on a grid and hope. But anyway, you sort of put them on a grid and see if you have 3D crystals. Set up low dose, set up diffraction mode. Take an initial pattern of one of your crystals, and if it goes well, then you can set up for full tilt data collection of that crystal. So yeah, you're still stuck can be stuck a little bit at the screening stage. So, for X-ray crystallography, that's not a problem. I think you screen pretty quickly by seeing if you have crystals or not. Are they birefringent? Do they look like real crystals? And I think now beamline time is not so expensive anymore. So you can actually do all your, I think a lot of people just do their screening at the beam line. Just take, you get what you think are crystals, or you're pretty sure are crystals. If you don't, even if you don't have a home source, you take them to the beam line, you put them in, if they diffract well, you collect the data set. If they don't diffract well, you just go on to the next one. It's still a very fast experiment. You know, EM is not like that. EM, if you have to screen by negative stain, or you have to screen, you know, once you actually have crystals, you plunge screen them, you have to screen for good conditions for plunge freezing, you're limited to a few grids a day. And you know, the screening process is much slower, as if you've ever done EM, as you know, because you can only put in so many cryo grids in a day. I suppose if you have an autoloader, you can put in 12 grids and go through them fairly quickly, perhaps. But still, the screening method is still much worse or slower than for X-ray crystallography. You then have to have your scope aligned well for low dose electron diffraction. So basically, it's not that hard to do, but you do have to make sure that the optics are good for diffraction mode. You don't have any diffraction astigmatism. It's all sort of it's an alignment that's done a lot because a lot of people aren't caring to collect diffraction patterns. But if you are, you have to make sure that it is well aligned for diffraction imaging. You make sure your sample still has to be eccentric when you actually find your crystal, because otherwise, when you tilt it, it's going to swing out of the area of view, and you're not going to have a diffraction pattern anymore. And so what we usually do is you sort of set up the low dose mode of the microscope to screen at low mag, just to find the location of the crystals, and then you store them in the microscope itself. You know, the microscope has an interface for storing stage positions. You could do it with other software too, I guess. But so far, it's sort of been enough of a niche thing that as far as I know, there's no sort of automated way to do this, unlike for single particle or tomography. And then you also want to screen at a pretty low dose, so 10⁻⁶ electrons per square angstrom per second. And this is, you're at a low mag, so it's naturally going to be pretty low dose. And then you can sort of look at the crystals. You then set up the microscope. You can set up this overfocus diffraction mode, where you sort of, it's in diffraction mode, but you can sort of crank the focus so you actually, instead of seeing a diffraction pattern, you see an image. And that just sort of gives you a very high contrast imaging at very low dose. So that's sort of, that used to be the old way of doing low dose imaging, where you would sort of set up in this sort of overfocus diffraction mode to sort of, it's sort of like giving it a very high defocus. It's sort of what it looks like. Essentially, it's kind of the same thing. And then you sort of, because the scope, the low dose program of the scope usually has 3 modes. What's called search, so you would set that up in low mag mode, focus mode, which would be this sort of overfocus diffraction mode, and then image, which would be in regular diffraction mode. But you would sort of find your crystal and look at it in sort of this high contrast mode, still at a pretty low dose to make sure that it looks good. Get the eccentric as perfect as you can, and then set up diffraction mode so that you put in a beam stop, and so that it's centered and it's blocked by the beam stop. You still want a pretty low dose rate, so 0.01 to 0.05 electrons per square angstrom per second. And then the beam, say we're around 5 to 10 microns in diameter, so it's enough to cover the crystal, but that's about it. You have a selected area, aperture inserted, which is approximately the size of the crystal, so you're not getting too much extra stuff. It's a circular aperture, of course, so you're not going to ever match the shape of the crystal, but just the approximate size. And then collect let's say an image for a few seconds. If you see high quality diffraction, then you go and collect a tilted data set. If you don't see high quality diffraction, then you just go on to the next crystal, of course. So it's a very manual approach. So for single images, which is what was done first, it becomes very much like tomography. You go into in half a degree or 1 degree increment. You can adjust the exposure time depending on the sort of the spots you're seeing. You generally want to be, usually you're using a CMOS camera, so it's a high speed sort of modern camera. It's not a direct detector. It doesn't have to be a direct detector camera, but you want it to be fast enough that you can ideally take a lot of images quickly. And the CMOS cameras are quite good for that. But if you only collect images, because of the Ewald Sphere problem, you only have partial reflections recorded for most of them. So what they first of all did when they did this was they figured out by tilting at a very fine degree which is the full intensity reflection for each of the reflections, and then just use that. They had to write their own software for that, so that became a complicated processing thing.
I feel like that problem exists at the synchrotron too, doesn't it?
I don't know.
I mean, partial reflections. I mean, that's why you have to index. And
Right.
You
Yeah.
have to, merge and scale.
I think it's worse for this because even you might be getting only partial reflections for some of them, but at least some of them, I think it's going to be more complete because you are collecting at least a little bit of oscillation, versus just a complete flat image with no
you're right.
movement at all.
Yeah.
But I think you're right. You do get it is still a problem in X-ray, but I think it's better. It's all better worked out. So the original one was a LISA design with 2.9x in resolution, and it was on a 200 kV scope on a TVIPS F416 CMOS detector, which is a good. It's not a direct detector, but it's a very high quality camera. And then this is sort of what their crystals look like when they looked at by light microscopy. So the ones shown by the arrows, which may or may not be visible, they're these tiny little dots. These are the ones that you want to image by MicroED. These ones you want to image by X-ray. So you are looking at very, very tiny crystals. And this is what the image looks like. This is a sort of a real space image in the microscope. So this is probably done on a quantifoil grid. I think this is a 2-micron hole here, and then this is the crystal itself. So then, and this is the scale bar is 1 micron. Yeah. So this is sort of what you're imaging. So you would set up your SA aperture to sort of cover this, and this is like a flat, wide crystal.
Do you expect the diffraction to be exactly the same if you take if you go to the X-ray beam, if you go to the synchrotron, or if you do MicroED, like, do you think it would? So
Well, I think you'd see. I mean, it's a different wavelength, so the sphere is different, but the spacing and all that's all the same.
The
So
unit,
the units, that will all be the same. Yeah.
but the actual how far out it will diffract to?
That actually, I mean,
What would
that
be
can go further. I mean, by this, I think, because your wavelength is so tiny that you can actually, if your crystal is high enough quality and your imaging is, your ice, I guess, is thin enough and everything is thin. I mean, they've seen like 1 angstrom. I guess X-ray has gone further than that. It depends on what wavelength you're using in X-ray too. And
Depends on the detector probably too, right? Because they fall off. The intensity falls off the scattering.
right, yeah. I think with X-ray it can be a problem that you can oversaturate your detector sometimes. With this, I think they said it's never been a problem because I guess you're getting a low enough signal normally that you don't have to worry about the dynamic. It's been enough to still always be within the linear range of the dynamics of the detector that they're using.
And do the crystals degrade at the same rate?
The electron beam is less harmful than the X-ray beam. That's sort of why you need. I think that's why you need a bigger crystal. It's my understanding, because the bigger crystal you get more. You have a lot more to damage. So I think technically, if you look at Henderson's paper from 1996, he was sort of going over how the E-beam is less harmful than the X-ray beam to these crystals. But the thing is, with electron imaging, you're sort of limited with so much fewer particles or unit cells. So it's like with a typical 3D crystal, you're in the 10 to the 9 to 10 to the 12 range of scattering things. Whereas by single particle, 10 to the 6 is big. I guess by this, it's probably more, maybe 10 to the 8 or just 10 to the 9. I don't know. You'd have to figure it out. But I think technically the E-beam is less damaging to the crystal than the X-ray beam. X-ray beam has a lot of energy. So in this original paper, what was good is they actually figure out what they call the critical dose. So this is like accumulated dose and looking at the diffraction intensity over time of 3 different spots. And it seemed to be more or less constant until they got to a total dose of 9 electrons per square angstrom. And at that point, the intensity started to drop off. So they sort of figured that they limit their total dose throughout the entire tilt series to 9 to 12 electrons per square angstrom. So it's always still a very, very low dose imaging. And in a way, this sort of agrees with, with our low dose single particle, imaging. Quite often you're sort of cutting off below 20, above 20 electrons per square angstrom, you certainly should be dampening the high resolution information. So that's why they do all this sort of fancy dose weighting.
But that's total dose, right?
This is total dose. Yeah.
So that would be, for single particle, you'd probably be an order of magnitude above this.
Indeed, yes. For the whole picture, yeah, we're normally shooting around 50 to 70, but now we also can fractionate the dose.
Yeah.
So we're a lot better than we used to be. We used to be, if you just took one image, you were sort of trying, quite often people were trying to limit themselves to 20 electrons per square angstrom for the total dose, which to sort of not destroy the high resolution information, but then it made the thing almost impossible to see. So this is one of the wonderful things that the new cameras give you is to be able to fractionate the dose. You can give it 70, but then you can only use you can still use only the high resolution information from the first 10 or 20. Oh, and here's a movie of their from this first set, which was taken at 1 degree increments, and then the diffraction squats are circled. So you can't actually. Yeah, you can see some of them, but not very many. These are the ones that were sort of found by the software.
They actually solved the structure of it.
Yeah, this went to 2.9.
It doesn't look like a typical diffraction pattern.
It might be very weak, and if it might be also sort of masked by the circle.
Yeah.
I think so. You only see the very intense
Yeah.
reflections.
Yeah, I went to the course
So
two
not a
years
great
ago.
demonstration, fortunately, but
Well, this was the first one.
It's almost like take our word for it, they're there.
They solved it. Oh yeah, so this sort of showed the limitations of the sort of partial diffraction by their imaging. So this is the same spot, and then it was sort of pretty weak, and then they had the full intensity at one angle, and then they tilted another 0.1 degree. This is minus 0.1 degree, 0, and 0.1 degree. And so this is sort of the problem of the partial reflections, where this is all the same reflection here. So if you oscillated it, this all would have been integrated. But because it wasn't, they sort of had to had to figure out, okay, this is what the intensity should have been of this spot. So the better data collection is continuous rotation, where you rotate at a continuous rate. So that unfortunately, you sort of need a hardware trick to do that, because none of the stage controls actually, they let you tilt to a certain angle, but the manufacturers never figured that anyone would want to tilt it at a defined rate. So you have to figure out a way to tilt it continuously at the same rate throughout your collection. And then you have to have a camera that can be in a continuous mode. For this F416 camera, it's called roll and shutter mode. So it's sort of it's no longer shuttering the beam, it's just collecting. It's a CMOS camera, so it sort of collects in rows, and then collects another row, You have to figure out what the right rotation rate is. If you have a high rate, you get more effective oscillation on each frame, because you're going to fill in more space. But then if it's too high, you're going to have overlapping spots as the different ones come in. If you have a low rotation rate, you're going to get the weaker spots more visible, but you're going to might get too few spots per image, and so then that's a problem. You're continually dosing it throughout the entire exposure, so you only have, say, 10 electrons per square angstrom altogether before the crystal's dead. So you sort of have to set it to the right rate. And what they did, first of all, was actually on the Tecna F20, you have a little, on the stage itself, there's a alpha button that lets you tilt it. And so the harder you press that button, the faster it tilts. So they came up with a little weight, and then they put this little weight on it that weighed the exact amount to tilt it at the exact rate that they wanted. You can now buy something for the microscope that will let you do this continuous rotation. I should say that downstairs on our F20, ours is sort of set up the same way. We have a f416 camera in addition to the DE camera, so we can do this sort of experiment. But we don't have the continuous rotation thing, but I found a little weight that is the right weight that seems to rotate at about the right speed. But we haven't done too much of that yet. Yeah, so a little more tech details. So most of it was basically almost all of it has been collected on a TVIP's f416 camera in world shutter mode. You have continuous readout of the parameters are disabled. So in the processing software itself, you have to define where the beam center is, because it might not be the center of your image. It's just where your diffraction spot actually was aligned, which hopefully is close to the center of the camera, but it may not be the exact, probably won't be the exact geometrical center of the camera itself. It also could change because of microscope instabilities. As you're imaging, it's possible the diffraction spot's going to wander around a little bit, and so then you sort of have to align it. You have to, when you actually do the processing, you have to tell it where the center of it is. You have to know the rotation rate of the stage, because that's also not recorded in all of these images or movies, so you have to know that, okay, I started here, and then I ended here, and I rotated 50 degrees in 10 seconds or something like that. And so then you figure out the frame rate of your camera so that you have to then calculate what the theoretical tilt is of each little image. So that does give you a little bit of error there. And you have to know which way you rotated it. If did you go from -60 to +60 or vice versa? So you need to know the direction, because you could mess that up. And you also have to know the virtual sample to detector difference. You have to sort of calibrate the microscope so that you know the sort of diffraction distance of it to the sample. They have software that converts these f416 movies to this SMV format, which is like a Super Marty view, which is commonly used in X-ray crystallography. It's supported by these other programs, Dials, MOSFilm, XDS. I'm not familiar with them, but I guess if you do X-ray crystallography, you'll probably know them. Yeah, so basically, because of the lens magnification, the physical distance to the detector is different than the distance to the virtual detector. Because you have your sample here and you have your detector down here. You're taking a diffraction image, but you're not doing direct diffraction. You can't just measure that distance. But what you actually do is you put in a gold sample or something like that with a known spacing. You measure the spacing on the camera, and then you can figure out the distance. So that's a calibration that has to be done. It's not very hard to do.
Wait, why gold?
Well, because this goes gold diffracts. You can get a gold lattice too. The spacing is pretty well defined, and you can just buy a gold crystal sample. It could be something else. It could be graphite or something, but gold is pretty commonly used in EM for calibration, just because it's easy to get. I guess you also have to figure out the gain of your detector, make sure that the gain is all set right. You can look at, there's some software you can do to look at the background intensity outside of your diffraction spots. The camera doesn't label which pixels are hot or dead, because you're sort of collecting it in this movie mode, so it's not really the ideal mode for the camera. But on the other hand, hopefully as long as it's not too bad, you should be all right. You shouldn't have too many hot pixels in your camera. And yeah, the other good thing is that because the patterns were collected at low dose, they said they've never gone outside the linear range of the camera, so that's kind of a good thing. So indexing of it, basically once you collect your images and move them into a standard X-ray format, it becomes, I think, virtually identical to standard X-ray processing. You have to know the wavelength of the electrons And the complicating factor is the flatness of the Ewald sphere because of the small wavelength. So each orientation is almost planar. So you sort of get less curvature than you do in the X-ray patterns. So what practical terms, what they found was that if you collect 5 to 10 images spanning about 20 degrees, the auto-indexing tended to work pretty well. I went to a course 2 years ago, and that's pretty much what we did, and it worked. I think it was with lysozyme, and it worked pretty well.
So do you overlay those, or you need to collect at least 20 degrees for the auto-indexing?
Yeah, you need to collect at least 20 degrees. So usually they didn't really, in one experiment they generally didn't collect the full 90 or 140 degrees because the crystal would be dead by then, but they tended to collect about 50 degrees or 60 degrees. And then with the knowledge that the last ones, the high resolution spots would start to disappear. But yeah, you sort of get this whole, you just sort of define which ones you tell the first bunch that you want it to index. And that seemed to work pretty well. It seemed to be pretty automated where it's been a couple of years since I did it, but you just sort of told it and it just sort of blah 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 and figured the indexing.
Yeah.
Of course, it helped that we already knew the indexing, so you knew if you got the right answer or not. If you're doing something novel, then you probably have to be a little more careful. But the other thing is the sample orientation is sort of a calculated orientation, determined from how fast you rotated it and the timestamp of the image. So there's a bit of error there. So that also has to be corrected. I think the software did that too. I think you gave it initial estimates, and it would then sort of. I think it sort of refined that somehow. It's probably also done in X-ray. I'm not sure, but I think it refined the angle. And then the other thing is the error in crystal orientation. So there's this thing. I guess there's this factor called mosaicity when you process it, which takes into account like the imperfections of the crystal or different spacings in the same crystal. They sort of, the way they run the software, they sort of throw all the errors into the mosaicity. So it's no longer really a measure of mosaicity. It's just more of a sink to throw all of the errors in, and that seemed to work. But then it didn't become a meaningful value. But
It's seldom used, really. I mean, I don't think
Yeah.
about mosaicity really as anything other than
a sink. Maybe you always use it as a sink for all of the bad values. I don't know.
you want to set the parameter big enough so that it includes everything, basically. Like,
Yeah.
because if you have a really elongated sort of diffraction pattern or diffraction spike, you want to include all that. So maybe that's what matters.
And then for phasing, most of the structures they did it through molecular replacement. So that was again standard X-ray crystallography tools. But they did for this highest resolution peptides, they did ab initio, and then they said they needed to get the fraction to be at least 1.4 angstroms or better, and they were able to do ab initio phasing of these tiny peptides, and those are the ones that went to like 1 angstrom resolution. The larger proteins they did all through molecular replacement.
Wait, so why not just take an image, like in 2D crystallography?
The phases are not going to be accurate.
Yeah, you're sort of. I mean, I think that's a more
We said
experimental
a single layer
technique.
versus many layers, remember?
Yeah, it's no longer. It's not a 2D crystal. It's a 3D crystal, and you have to figure out which spot is which in the diffraction pattern. And I think they're working on that. And actually,
Like a
there's.
starting point, though. I mean, like, is there a...
Yeah, the thing is also you can't. I mean, with your image, in order to collect an image to get phases, you have to give it a higher dose than you are for the diffraction.
Well, that's
So
what
then
you
you're
do.
gonna-
Yeah, you just pick one.
So you'd have to have
crystal
it
just for...
just for that, and
yeah.
then you'd have to figure out how to merge that and figure out what. I mean I think that is probably going to be a way of the future to do it, but the way they're doing it now, they haven't done that yet.
I guess maybe you mentioned this already, but it's a projection, right? So to get like 3-dimensional phase information, you want the 3-dimensional transform, or so the 3-dimensional image, I guess. Maybe if you did a tomogram first, then then you might be able to get the phases, I guess. I don't know.
Yeah,
Reconstruct the crystal itself, I guess.
perhaps. Yeah.
Yeah, I don't know.
I mean,
There's that.
basically the phasing problem is a problem. They've only apart from the ones where they've done for ab initio, these small things, they've only done molecular replacement. They, in theory, I mean, you should, yeah. Actually, I have it here. Where there's a paper in 2013 where they were sort of doing images of 3D crystals, and they did sort of standard 2D classification of them, and then saw these different, different projections. That you could maybe do something like that, where you sort of image it. Maybe you can do classification and work that out to get the phases, but that hasn't been done yet.
Or you could just, can you just take one crystal, like tilt it to the maximum, and then
So do a tomogram or something.
but you don't need to do a whole, then you just need like one image. You
I'm not sure how
technically
many
only need
phase.
one
I'm not
image.
sure how many. I mean, well, one image is only going to have a limited number of spots, right, from this 3D crystal. So I'm not sure how many estimates of the phases you need to start with. Whether just from one sort of plain image is enough.
Because I'm saying if you, yeah, I hear, okay.
Because you in order to, the full experiment is this whole series of images which has there's many spots, and I'm not sure if you only have one or two of them where you have estimates of the phases, if that would be enough to jumpstart the process or not. I haven't done that myself, so I'm not sure.
When you do phasing, because you still need redundant sets. Sorry.
No.
When you do any sort of heavy metal, like.
Oh
it's-
yeah.
Does that work with
It gets-
electrons?
Well, that's another idea.
Because
Maybe
anomalous
you could-
diffraction, right?
I don't
know if electrons do that. I don't know.
That's something that they also mentioned, future direction. Can you add heavy atom derivatives to do this or not? And, or can you get direct phasing methods better so that if you had to, could you phase it better ab initio with bigger crystals than with these small peptides? Using 3D, using images for phasing. These are all sort of future directions that they're definitely looking into. But to my knowledge, they haven't solved them yet, but they are trying
Heavy
to.
metal, it's like, because the source is different. It's very defined as the K edge for each of the.
Well, so heavy atom
cells.
soaking probably would work because you're taking, in that case, you're taking the difference in diffraction patterns. Certainly there should be if you have heavy atoms, but
You have to shoot it with different wavelengths.
no. So you're talking about like the SAD, right? You're trying to get anomalous information. That may or may not work because electrons might not act like X-rays, I guess.
Well, you could. Yeah, the thing is, you can change the wavelength by changing the voltage.
Yeah.
But then you'd have to realign the whole scope, probably. I mean, maybe if you only change it by like one few EV or something like that, I'm not sure. I mean, that's something that.
Well, aren't those parameters pretty set for each heavy atom, like the K edge for each of the.
I think
Those
it's
are
set for.
pretty set, so that shouldn't.
That's X-rays.
But that's for X-ray. But you have to figure out how much of what
But a
voltage
source of
change gives
energy
you
should
that.
not be different. Like, I mean, if it's a certain amount of energy, shouldn't that be the same, no matter what source? Like, does it act differently when it interacts with the sample itself?
Well,
Like the way
yeah.
it scatters it, it's very different.
Yeah,
You're
very,
saying,
very
yeah.
I
different.
mean,
think it's a
anomalous
different
diffraction is you disturb the orbitals basically, right? So the electrons change orbitals, and that's how you get the signal. So what creates that? So is it an X-ray that sort of bumps electrons to different orbitals, or is it electrons themselves that is going to change? And it's probably, I mean, I'm not a particle physicist obviously, but energy should be factored in to some degree, but it's the nature of the particle that is sort of creating the collisions to produce the anomalous diffraction. That that's why it's uncertain whether electrons can actually do it. X-rays can accomplish that efficiently, depending on the heavy metal that you're using, but it's not the same thing.
Yeah, you might be. I mean, with the maybe if you have an energy filter, you might be able to do something clever with that. Like if you look at, you might be able to pick up some anomalous signal that way. But I'm not sure.
Actually, you're right. It will be different is the scattering you're getting from different things. From X-rays, it's scattering by what not the electrons are. With EM, you're scattering electrons.
Yeah.
But with the X-rays, it's being scattered with the
Yeah.
So you're right. It's not right.
Have you heard of a atomic form factor for EM, like you do in crystallography? No, right? Okay.
Yeah, they have figured it out already. So
Okay, is there an imaginary component to that form factor? 'Cause
Yes, there
mathematically,
is.
that's what gives us the anomalous.
Yeah, if you can break the Friedel path, yes, you can. If you break it, you get Ewald Sphere curvature and problems like that.
Yeah.
Yes.
So maybe?
I think it's something to work on, yeah.
Yeah.
But not yet. No, they haven't done it yet, to my knowledge. That they published.
Yeah, we need to figure out if electrons can scatter and break Friedel symmetry for other reasons than thickness. So you're thinking about the other
They can break because you have different planes of Ewald Sphere curvature.
Yes.
So they have a different plane of imaging. So they break because of that.
Ah, you're right. Yeah, this is De Rosier and
Yes.
Grigo shows
It's
this.
not true.
Oh, right, the paper's in
Yes.
Oh yeah, so this is one sort of interesting thing I thought was like in this their highest resolution map they said they could see the proton in it, which is they could see 5 of them in this map, which is pretty amazing from an EM experiment.
Or crystallography, but that's crazy.
So there's basically they did give them extremely high quality maps of these small cores of amyloid proteins. So it is a pretty, even though it's a niche technique, it's a pretty cool technique. And I would say, if you want, we're interested in doing it here. Like Anchi and I went to the course a couple of years ago, and it was pretty good to learn about, but we haven't had any driving projects yet where someone is like, oh, I really want to do it, and I have crystals. But once we get it, you always need it, for any new technique, you need a driving project, and then it sort of gets pushed along.
I'm sure you can just go up to Compa and see what failed projects that they have over there and just find their crystals, I guess.
Oh yeah, so I guess in summary, the technique does have some advantages. You don't need high-end equipment. You don't need to get a Krios and a K2 or a Falcon 3. So 200 kV, these are all done on 200, for the most part, 200 kV FEG microscope, which is now, I would call mid-range. And a CMOS detector with movie mode, which also is not extremely high-end. They're not like cheap, but they're certainly affordable by a lot of more places than a Krios. Probably the scope alignment is a little less difficult than for imaging. It's like the diffraction alignment is a little simpler because it's a simpler experiment. I guess probably the best advantage is the highest resolution you can achieve by Cryo-EM, and then also the processing software, which is basically X-ray software, is very mature and well understood by a very large community. So I think unlike say for 2D crystallography where it's a very small community and you don't have that many people to help you, with this one you would have all of X-ray people. Once you convince them that you're not, this is EM's electron scattering, not X-ray scattering. But I think they have built the X-rays electron scattering factors into a lot of the software now. Disadvantage is obviously you need crystals, and screening is slow, so that if you don't have crystals you can't do it, or if the crystals are invisible it's hard to screen. But you sort of have to, I guess, hope, or once you get crystals though you're okay. The crystals do have to be small and ideally randomly oriented so that you can fill in everything. You need a very high quality stage, and you'd be able to do this continuous rotation. So that's a bit of a limitation. If you have a bad stage, it's just not going to work. If you're tilting it and it's always moving out of the field of view, it's not going to work. So everything the scope still does have to have some sort of good quality. The phasing problem basically is right now it's molecular replacement unless the quality is extremely high and you can do some sort of ab initio method. But again, that hopefully is the future that you could do some more clever imaging and get phasing from that. But no, it hasn't been worked out yet. And then there might be a maximum size of the molecule too, but if it's big enough, maybe you don't have to worry about crystallography anymore. You just do a single particle. So, this seems to me a technique that's good for small things that would be sort of too small for single particle.
or flexible things that you can coax into a certain configuration.
Yeah, yeah.
I've
It's
seen
flexible,
that.
but then the crystal locks it.
Yeah, I've
somewhere.
seen that like
Yeah.
a lot. Yeah.
But then you're at the thing, how do you know it's not caused by the crystal?
It's better than no structure, put it that way. You have to do your due diligence in biochemistry, obviously. But
Okay, so that's sort of the end of this one.
Has anybody tried LCP crystals for this, or were they all vapor diffuser? The cubic phase crystals.
Oh, the calcium pump as the one paper that has been a membrane protein. I don't think it was cubic phase. I think I think then that becomes sort of hard to pipette or something. You'd have to be able to pipette it onto a grid. It might be hard to deal with, but I'm not sure. But in general, I think the ones I work. No?
I mean, it's sort of like a paste, but you can potentially still put it on a grid.
Yeah.
Especially, I mean, it depends also what lipid you use.
If it's very
the
right.
cubic phase might be sort of watery.
But if it's very viscous, then you'll have trouble blotting the thing too, I think.
Yeah.
But you have to blot it so the ice is thin enough.
you can fish them out, right? I have no experience with this, but you're able to fish them out.
Yeah.
You can potentially do like a buffer exchange into
Yeah.
cryoprotectant or
Yeah.
whatever.
Yeah.
Yeah.
And once the crystals are formed, they typically don't need the layer that
Oh, they're pretty resilient to being moved outside of the.
yeah.
Because usually you
I mean, there are
transfer-
crystals
Yeah.
of a cubic phase sort of. So that they don't need the supporting sort of crap around them once they are formed.
Yeah, I think the only membrane protein. Look at that list again, but I think it's just a calcium pump, and I don't think that was cubic phase. Yeah, it's just the calcium pump, and that would just sort of like to form these very thin 3D crystals that were only a few layers thick, and then managed to get some tricks to make it a little thicker.
That's pretty encouraging. They can solve P1, right?
Yeah.
Even with the missing wedge and all. That's great. Just going through my mind of all the things I've tried to crystallize that potentially have microcrystals in.
You still have an issue with the heterogeneity of the crystal. Like you might get a crystal that still may not diffract great if it's heterogeneous.
Yeah, it does still have to be a high quality crystal, but I guess the thing is, hopefully if it's small enough that you're going to decrease the amount of heterogeneity than if it's a bigger crystal, which way it might
Like
be.
presumably the reason that they can't crystallize at all most of the time is because of this heterogeneity. So unless we're saying that like it's a way that you're filtering out the pure parts that are okay. Yeah. Sorry. Yeah. That's
So I think
basically
you're talking
the,
about length scales, right? Like I've seen crystals personally that like will curve like this, but then like on that small enough scale they'll be ordered.
right. That's what I'm saying.
Yeah.
Like this, the ones that are similar enough will crystallize,
Yeah.
and the ones that are not just
Right.
won't. But it's
Or might like poison itself somehow. Can't continue.
Somehow
Well, that's what these
you're
little
averaging
peptides are.
the
They
whole
basically
crystal essentially,
they
right?
cause the
So-
structure of it seemed to cause some sort of strain. It couldn't grow big enough. These
what you're saying. Like if
this
it's,
this synuclein, these ones with these small peptides that they saw.
yeah, they tend to.
They were unable to form a big, well-ordered crystal.
They tend to aggregate. That's what alpha C.
Yeah.
Crystallography is also a field full of anecdotal evidence that can come up with the counterexample and an example for every sort of phenomenon it seems.
It's more
Who knows?
qualitative.
As long as it diffracts, I guess.
Okay.
Sweet, thank you.
Let's thank Bill again.
Do we have everything we need to do this here?
We do.
You do?
We do.
Do you need a project?